Cin Ty was born in Taiwan and raised in Southern California. He got his bachelor's degree in 1996 from the University of California in Berkeley. He then went to Harvard and did his PhD under Roberta Rudnick and completed that in 2001. And after completing his PhD at Harvard, he went to Caltech for a year and did a postdoc. That was a good place to do a postdoc. After that, he went, I guess, right to Rice University.
Mm-hmm.
And right now, Cin Ty Lee is the chairperson in the Department of Earth and Environmental and Planetary Sciences. Now, the reason why I invited Cin Ty to give a talk here, I mean, we go back a long time, and we read our papers, and I greatly admire him. And he is one of the, I think, few solid Earth people who has done an excellent job in trying to understand the importance of the solid Earth in affecting long-term climate and even the great oxidation event. So he's really, thinking in terms of the systems approach. And today what he's going to talk about is, okay, it's origin, a little bit slightly different title. But the other thing that's actually pretty well known about Cin Ty is that he has a passion for birds, and he paints them on the professional level. And if you want to check his stuff out, go to his website and you see what he's done, and it's amazing. He's a great artist, and his prices are reasonable. And what I'm going to do is give you this little gift so you can remember this. Now, so Ying Reinfelder just gave this to me, and I wasn't aware in the past that how much memory this little thing holds.
I heard different stories.
It's about maybe 60 gigabytes, 48 gigabytes. But if you look at it, it looks like it's a bottle opener too.
It is a bottle opener.
It's a bottle opener.
It's a beer opener as well as a flash drive.
Now,
Put on your keychain.
why did I not get one of these when I gave my So, welcome to Rutgers.
Thank you. Okay, thank you, Claude, for inviting me and giving me such a generous introduction. I'm very happy to be here at Rutgers. I know many of the faculty here by name. Haven't met many of you before, but it's a great department. Is that me? Oh, okay. So thank you for inviting me. And so the title of my talk is Origin and Evolution of Continents, but I will be talking about how the formation of continents, basically the whole life history of a continent, from the birth to its sort of demise there, and how that may influence the surface environment in terms of climate and maybe even biogeochemical cycling. So I want to start off with three observations that I'm kind of obsessed with now, and they're observations we often take for granted, very simple observations. And the first one is just, this is the hypsometry of our planet. It's unique. We have 4 kilometer deep ocean basins, and then we have our continents, which turns out most of the continents lie very close to sea level. And then you've got this little tail here, which are made up by these orogenic belts, these Tibet and the Cordillera, and of course, where you have a thick ice sheet, you'll have high elevations. But for the most part, we're near sea level. And we have these two, we don't have anything in between. Why do we not have anything in between in terms of elevations? So that's one. And the other one that is in textbooks, of course, is, so there are deep ocean basins here. This is the oceanic crust, continents here. They got a thicker crust beneath the continents. And they have different compositions. One is basaltic and one is granitic in composition, more silica, less iron than what you get in the basalt. So why this bimodalism in terms of the composition of the crust that sits on the surface of our planet? And then the third one, which may not seem even related to the first two, but it will become relevant near the end, is something that I've become fascinated with, which is these things called the great unconformities. And here, this is in the Grand Canyon. And here you have these 1.4 billion-year-old basement rocks. They're metamorphic rocks. They're magmatites, which are forming in the lower crust, melting of the lower crust. If you were to walk across them, you would find that you could see these melts looking like they were just squirting around just yesterday. So somehow they've been brought up very fast, eroded, and preserved so they don't retrograde so that you can see them. And then on top of them lies Paleozoic sediments. And you've got basically a billion-year gap in terms of the history here. And these Paleozoic sediments are marine sediments. So why is this of interest? Well, in order to get a lot of erosion, you had to have potential energy, so you had to bring these up very high, so they were at high elevations, probably in a mountain building event. And then these mountains somehow must come back down and form basins to collect sediments, become depot centers. And so that's what I'm very interested in. And so there's missing information here, but it's sort of like looking at somebody's diary. I just grabbed this. This is John Wilkes Booth's diary. He assassinated Abraham Lincoln. And of course, you want to know what was going on in his mind to figure out the whole story, his motivations. And you can read his diary, what he said. It doesn't make a lot of sense. But you can also look at this part, which is he didn't put anything in those days. Those are like the missing information. The pages were ripped out, or what was he doing during that time? And that may tell you much more about his personality than even what he writes. So what's missing in here, that's the story that I want to get at the end of this talk. Okay, so to get at that, I'm going to start with this question. What controls elevations of continents? The first thing I'm going to show here is a gravity, free air gravity anomaly map of the Earth. And if you ignore the Hudson Bay, where the ice just melted and you have, it's not isostatically compensated, you look at these places, take a look at Africa, which is fairly high elevation, and then go to the mid-ocean ridge. They actually have the same free air gravity anomaly. In fact, go to the middle of Tibet, which is more than 4 kilometers high, and go out to here, which is 4 kilometers deep. They look the same. The edges don't. Those are edge effects, so don't worry about those. What this is basically saying is that there's no excess mass beneath any of the regions, at least on long wavelengths. So it means that all the continents, all the elevations on long wavelengths are isostatically compensated. And so when we recognize that, it's all about buoyancy. And then the questions are, what controls the buoyancy? Density, the crusts are low density, that's one thing. Crustal thickness increases the buoyancy. So size matters, ocean volume matters, mantle temperature matters as well. All of those come into play in controlling the isostasy. So to first order, if you look at elevation versus crustal thickness, and this is just the MOHO depth, from the surface down to the base of the continental crust, what I've got is some of the main mountain belts on our planet, and then I put the oceanic crust right here. And you can see, you put them all up, they form on this trend indicating that elevation, 90% of the signal in elevation is controlled by the thickness of the crust. These different lines right here are different densities. And we often talk about, and I've made the same mistake before, that the reason why continents rise high is that they're underlain by granite, which is less dense than basalt, which is partly true, but that's not the main signal. It's crustal thickness. The reason why ocean basins are low is that they're only 10 kilometers thick, and continents are high because they're really thick. Okay? And so this concept is basically area isostasy. It's no different than thinking about an iceberg analogy for continents. The tip of the iceberg is underlain by a thick root. So if you have high mountains, you have a very thick crust. So it's all about crustal thickness. So if you want to understand how continents are formed, even though I'm a petrologist, it's not about how you make granites, it's how you make thick crust, okay? And then as a petrologist, the question is, how does that thick crust influence composition in the future? So the question of what controls the thickness of a crust is, I try to keep things really simple. This is the thickness of crust as a function of time. Well, it's just the forcing. It's magmatism being added, or tectonic compression, minus the erosional effect that comes off the mountain. That sort of thins the crust, and those compete against each other. And of course, because of gravity, the higher you build it, the thicker you build it, the higher it gets. And the higher it gets, the faster the erosion comes down. So this erosional term depends on elevation or crustal thickness. And when you have an equation like this with a negative feedback, what that basically means that with time, if you're forcing it with this erosional response, you will get to some steady state crustal thickness that just is a ratio between how much you're forcing it divided by the efficiency at which you take it down, which is the efficiency of erosion. Okay? And the time you take it down depends on some kinetic rate constant of erosion modified by an isostatic component. So this is just showing that here. I've done some just simple forward models just for concepts. This gray line is showing a sudden increase in magmatic forcing, step function. And then this would be the response of erosion, the erosion rates. And depending on different rate constants for erosion, you'll see you basically reach a steady state where eventually the erosional flux, the exhumation rate, is equal to the magmatic production rate. Okay? How long does that take? Well, it depends. It could take anywhere from 6 to 10 million years, or even less, depending on how efficient the erosion is. And when you hit steady state, you will reach a constant crustal thickness, say this one, which I'm taking with a 1 million year response time. And that will then give you an elevation of 5 kilometers. If you want higher elevations, like 8 kilometers, then you're going to have either much higher magmatic forcing or less efficient erosion. Okay? All this is to try to get the point across that magmatism and erosion probably are very intimately linked, and you can't divorce them from each other. So one of the interesting things that is related to this crustal thickness is one of my students, Michael Farner, decided to do something almost silly, which was to just compile all the volcanic rocks in arcs and subduction zones across the world and plot them versus the elevation at which they erupted, which you would think, why would we ever do anything like that? And what ends up happening is you get this correlation, pretty strong correlation right here, that when the elevation gets higher, things get more evolved and more silicic. So this is granite and this is basalt. And if you go back to what I said before, that elevations correlate crustal thickness, because things are in isostatic equilibrium, you can convert this to crustal thickness. And what it's saying is that when you make thick crust, you make felsic rocks. And that is the reason why we want to look at crustal thickness. And so if you take that and say, well, this is right here, this range is the average composition of the continental crust today. As I said, they tend to be more granitic. Intersect that with this curve right here, it would say, without worrying about mechanism, that the continents are formed in a process that when they form, they are 50 to 60 kilometers thick. And that would correspond to very high elevations. Now today, like I said, most continents are down here at near sea level with a crustal thickness of about only 30 kilometers or so. So this basically what I'm going to say at the end, continents are born here through mountains and magmatism, and then eventually end up here. They would preserve their compositions, but their thicknesses and the elevations drop from erosion. Okay? So what's causing that? Well, we can go closer to in the North American Cordillera. This is the Sierra Nevada Cretaceous subduction zone system, slab going down, and then this is the volcanic arc that forms above that subducting slab. And one of my students, Jiang, went in to put together all the geochronologic data in there along with their spatial distributions of the plutons down in Southern California. And you show, well, these sorts of continental arcs have these flare-ups from, in this case, 130 to 80 million years ago. So this is an orogen of about 50 million years in length, when a lot of magmatism is coming and it's building new crust. And that area, we have xenoliths from volcanic rocks that come up that give us some insight of what happens as what the vertical architecture of these arcs look like. And basically you have all these plutons at the surface, and as you go deeper down, you have the dregs of the crystals that were precipitated out and allowing these liquids to continue to rise. And Claude Herzberg has worked on this as well. was one of the first to do this. And so down here you have all these cumulates, and I don't have time to go into great detail, but it extends down to 60, 80 kilometers in depth. And those cumulates are made up of these red and green minerals, garnet and pyroxenes. And what they show, here's sodium, magnesium, iron. These are all the plutonic rocks there. These are these cumulates. This is basically the trend that one takes in magmas to make the continental crust. And it's always been a mystery of what drives this. Basically, you need to take something out with high iron contents and low silica contents, and then the things will get more rich in the alkalis, richer in silica, and depleted in iron. Well, it turns out these peroxenites right here have the right compositions to drive you in this direction, garnet and pyroxene. But to form garnet really requires critical pressure or critical depths. And so this thing is gadolinium ytterbium. It's just telling you whether you have a flavor of garnet involved in the petrogenesis. So at high, if you go up, there's garnet. And again, we plotted this versus elevation, and you can see as elevation increases or crustal thickness increases, you start to see a bigger and bigger crustal signature. And at the same time, these are color-coded with silica content. You can see they're becoming more red, which is higher silica. And so the reason why continental crust is getting more silicic is probably related to the removal of these deep-seated garnet peroxenites that are only stable at high pressure. So to form continental crust, again, it's about really thick crust. You're not forming them in like mid-ocean ridges. You're not forming them even in island arcs. It's sort of continental arc environments. So I'll skip this one. This is not so important. And so different places where you form crust, mid-ocean ridges, that's one. Oh, it's not shown there. You have island arcs like the Marianas, but those never get to the thicknesses, 20 kilometers thick. They never get thick enough to make the silicic magmas. They never get thick enough to get much out of the water to get a lot of the erosion. But the continental arcs do, the Andean style scenarios. Those are interesting also for the amount of CO2 that comes out, but I won't talk so much about CO2 in this talk. So now I want to talk about the erosional part in building in the building of these magmatic or orogenic arcs. And again, this student, what she did, she wanted to look at the history of these volcanic arcs with time. And one of the things, because there's so much erosion that goes on during this magmatic forcing that builds up the thick crust, builds the elevations, and so forth, is that the tops of the magmatic bodies are eroded off. So you lose a lot of the information. Well, but if they erode it off, they go downhill and they're deposited in the forearc basin. And so these sediments, these turbidites here, really are the roofs of these magmatic bodies. So we go to these to figure out what happened before, if that makes any sense. And so if you look at these sediments, and this was done also off California in the Cretaceous forearc basement, these are the sandstones, and you can see there's a hornblende, there's quartz, a little bit rounded, but mostly angular, a very juvenile sediment. The hornblendes are fresh. There's biotites right here. Looks like this basically looks like I just took a granitoid and just crushed it up and just left it on the ground. So these guys come up and then they are transported to the deposition centers very quickly. Well, what we can do is, knowing the depositional age from fossils in here, but also then, and then from the exhumation, at the time that they form down here, from the detrital-zircon ages, along with the pressures at which they came from based on aluminum and hornblende, we can put some bounds on the rate at which this average rate at which each of these sediments exhumed from down in here out. Okay, and this is just the aluminum and hornblendes here giving us pressure. It's nice field work because it's right along the California beaches there, so she wasn't complaining about that. Let's see, and so this is what we get. So this gray curve right here is our magmatic production rate, which is based on those previous geologic maps that I showed you where we combined it with the zircon age data. So this is the magmatic forcing in terms of kilometers per year. That's the magmatic flux. These data right here are the erosional fluxes that we estimate from different age sediments. And the most important thing to see from here is basically confirming that you get this peak in magma. We just don't have data here, unfortunately, but once the magma kicks in, the erosion kicks in pretty quickly. In fact, on the same magnitude as the magmatic fluxing, indicating that there's a fast erosional response time, that these two things are coupled. Magmatism drives the erosion, actually. And in another talk, I will talk about how erosion then influences magmatism in terms of modifying the thermal state, but I won't do that here. And these curves right here are basically the model curves that we use to try to calculate what the response time or the average kinetics of erosion might be. And that will become useful again when we start to model the full evolution of elevations in mountains. So we get here that we're talking something like 4 million years for a response time or so, 4 to 8 million years for response time. So erosion kicks in pretty quickly. The other thing that is important is even after the magmatism stops, there's still remnant topography, so erosion continues. And there's a long tail where you'll have chemical weathering that is not supported by magmatic fluxing or CO2. Okay, so the conclusion here is a very simple one. Continents are basically born in magmatic orogens, and if it's all about thickening and the crust by the forcings and thinning it by erosion, then what actually happens is you predict a very strong correlation where what I call the orogenic trend is that when you're building the mountains by magmatism or tectonics, you'll go up along this line, and when you erode them, you should also go along this line too. You'll just come right back down right there. Now these are active mountain belts, so they haven't come down. So the question is, what actually happens when these mountains die? So this is the same plot with the same data, but now I put the rest of the continents elevation data on here, which include mountains, but also includes a lot of the stable parts of continents that have been sitting there for a billion years, like in the center of the cratons. I don't have any of the ice sheets on here. I took them out. And so you'll see that while the orogenic trend takes you up and should take you right back down, there's a whole bunch of the stable continents that fall off this trend. In a sense, their elevations are too low for their crustal thicknesses. Okay, so this is saying something else must be going on as the continents or the mountains mature, or as they start to die. Something else is going on. And this part is all about crustal thickening or thinning, and here we have a different story. Something beneath the crust has to be operating. And so that takes me to now going, we went from the surface, we go deeper and deeper, right? And now we're going to go, this is the moho. And of course, underneath continents, the base of the continental, of the continent really isn't just the moho. In fact, if you want to define the continents as being the cold parts of the surface of the Earth, the Earth's mantle is hot. So there's this thermal boundary there, cold thermal boundary layer that extends and penetrates into the mantle. Well, it turns out under continents, it goes down, depending on what age they are, 100 to 200 kilometers deep, this part being cold. And it's the mantle, it's made out of this green rock, olivine, same as the stuff in the rest of the mantle. Only difference, or the main difference, is that it's cold, okay? And if it's cold, we start to think, well, thermal contraction might actually be able to pull the stabilized parts of the continents down from this orogenic trend. So this is more evidence showing that they're cold. Temperature versus depth, these are zeniths. Here's the hot mantle, convecting part of the mantle, and the zeniths show that they're, they could be 100 degrees or more on average cooler than the ambient mantle. You can look at the seismology. This is surface wave tomography here, and the high velocities are these are transects across cratons. The blues are high velocities and generally interpreted to indicate low temperatures. And so to indicate here, you got a cold thermal boundary layer that extends to 200, 250 kilometers depth beneath most of the continents. Okay, so there's this cold finger underlying the crust. And these things, as you've probably heard Claude talk about in his talks and stuff, they've stuck around for a long time. Here's the crust, here's the continental mantle, here's the hot ambient mantle. And although you'd think that these things would be swept away and stuff, well, it turns out based on rhenium osmium model ages from these particular peridotites right there, they still preserve Archean ages, which roughly overlap with the age of the continental crust to within error. The errors of the rhenium-osmium modelings are very large. So it's suggesting that this feature, these things are formed probably in relationship to when the continental crust itself, this magmatism that makes the crust, is related to this process as well. But how is that? What is that relationship? You can zoom in more and look at the compositions of that lithospheric mantle. And this is just aluminum versus magnesium or sodium versus magnesium. The normal mantle is up here, and most of these rocks are way down here at high magnesium and low aluminum. All this is to say is that they underwent high degrees of melt extraction, which probably means high temperatures were involved to melt so much. So anywhere from, it could easily get 40% melting on some of these, whereas today, for most of the mantle, it's about 10% melting on average. So this is overly simplified, but the idea is how they may form. It may not necessarily be a spreading setter. It could be a plume. It could be an arc. It could be a lot of things. But the main idea is here's depth, here's temperature, here's the solidus. And when you have the mantle, which is solid, upwelling in a convective limb, it'll cross the solids and it will melt. Anything that goes above this will melt. The melt goes up to form basalt. The basalt then differentiates and forms granitic rocks like what we've seen in the Sierras. And then it leaves behind a residual that has the melt extracted from it there. And we can try to put some estimates on what pressures and temperatures the melting actually occurred for these peridotites. And this is, again, what a lot of stuff that Claude has done, that we can develop some thermal barometers on the residues right here. And I don't have time to get in great detail, but it's basically a combination looking at the magnesium iron contents of these rocks and developing a thermal barometer, and then one that is a measure of the melt fraction, and we have to calculate the melt fraction. And we solve these equations at the same time, and it gets you some average effective pressure and temperature of melting. So what you get here, and this is for that mantle, cold mantle finger that sits underneath the crust, is this. These are the current, or not exactly current, but these are the subsolidus metamorphic pressures and temperatures. This would be what the lithosphere temperature state looks like right now, if the xenoliths were sampled right now. And then these samples right here are the protolith pressures and temperatures, the conditions that they formed at 2 billion, 3 billion years ago. And I've drawn tie lines between those where I actually have samples where I can do both calculations. And so from that, you can see right here, they all show this slope, which is indicating that they formed at low pressures, at high temperatures, and then they have now been subjected to high pressures as they cooled. So they've been all, they had to all have been thickened in an orogenic event of some sort. So when it comes to how do you make the continental mantle, well, in fact, it turns out just like the continental crust requires a massive thickening event or a magmatic inflation, a combination of those. Instead of a simple plume scenario, it's got is something, I don't know the exact mechanism, but some imbrication of thrust sheets or just ductile thickening of lithospheric thickening that's not just in the crust, but also lithospheric mantle. It goes from something like this, an arc, and then becomes much thicker with time. Or you could have thickened this as well. The point is, thickening or orogeny, or orogenic thickening, is a feature that we see both in the crust and also in the mantle there. So we go back to the problem that it appears to be cold. And if it's cold, then it'll be denser, and that'll pull this down. But if it gets too cold, then just like oceanic thermal boundary layers, they will subduct and they should disappear. But these continents have stuck around for billions of years. So what actually allows them to stick around? So if you look at their compositions, and this is just the magnesium content, and then their densities, their intrinsic densities, the more melt you take out of it, the lower density they become. They become chemically buoyant. And so maybe they aren't negatively buoyant from the temperature. They are from the temperature, but it's completely compensated by a compositional effect. And indeed, this is what Tom Jordan back in 1978 suggested that this negative thermal buoyancy is exactly compensated at every depth by a compositional buoyancy such that it's completely neutrally buoyant. And so in the case when you're thinking about elevations and things, you don't really have to worry about this lithospheric mantle at all. But we know that this is not the case because the cratons actually fall at elevations too low for their crustal thicknesses. So what you can do to evaluate this is to say, well, so it turns out it can't be fully compensated. So what I've done right here is take the average densities for these peridotites in the cratons and with their average temperatures, and then calculate what the elevation would be for a given crustal thickness. And so that's shown here. So if you don't have a lithospheric root, you're going to be a cold lithospheric root, Cratonic root, you'll fall along this orogenic trend. But if you have a 150 to 200 kilometer thick cold root, it would shift all of these down over here to a different slope. And that could explain all of these guys. It's consistent with this, the cratons being underlain by a thick cold root is partially chemically buoyant, but not completely enough to offset its cold thermal state. So in the case of Jordan, he was overall right, but it turns out it's not perfectly isopycnic. So what you have to imagine is that you're still in net cold, and you're going to sink a little. So your continent is your rubber duck here, and underneath the continents, as they mature and age, an anchor kicks in that pulls it just a little bit down, okay? Hope that makes sense. So that becomes very interesting because the extent to which it pulls it down actually depends on how thick this thermal boundary layer can actually grow. And from the seismology, it appears that they're mostly about 200 kilometers. They don't get to 300 or 400 kilometers. Something's limiting how thick they can ultimately grow. And you can look, it turns out, and the question is, why don't they keep on growing? Well, this chemical boundary layer, this melt depleted layer, one of the things that we think happens is when you get all this melt out, you also dehydrate the rock of hydrogen. And what hydrogen does, it has this effect of weakening the rock. So if you take the hydrogen out, it strengthens the rock and makes it very viscous. And this is just showing you here that if you go from something that's wet, that's like a morb source, here's viscosity versus water content. A morb source right here would have a viscosity of like 10 to the, for this temperature, for example, 10 to the 18 pascal second. And if you dehydrate it to what we think Archean cratons might be, you can increase the viscosity by a factor of 10, maybe even a factor of 100. And that intrinsic strength may be enough to have some profound effects on the nature of how the continent behaves. And so work done by Katie Cooper, a student of Adrian Lenardic's, one of my colleagues, did something like this. This is how you have to envision the continents. There's a crust. This is not to scale. It's underlain by this mantle root, thermal boundary layer. But this green part is the part that was formed with the crust and is compositionally different than the mantle, both in terms of water and also the amount of iron and its density. And then this yellow part is the part whose compositionally identical to the rest of the mantle, which I didn't draw, but is just the interface between this rigid root and the convective mantle. So the idea is this is rigid and doesn't participate in convection. And so it forces the thermal boundary layer to be at least as thick as this rigid root, okay? And so the thickness of the thermal boundary layer right here, relative to this whole thing, the chemical boundary layer, is shown here versus the chemical boundary layer thickness, is basically saying here, these are some results from numerical models, that as the chemical boundary layer thickens, this ratio approaches 1, which is basically saying this convective sublayer doesn't really matter. That is, this depleted chemical root, which is rigid, it defines the thickness of continents, the continental thermal boundary layer. It will not get less, it won't shrink, it won't get thicker, it's just going to be sticking there for good. And for all intents and purposes, based on the rhenium osmium, it appears that once they're formed, they're there forever. They define how thick you can actually grow. Okay, so you might wonder, why do I care so much about it? Well, making continents, there's that orogenic path. So when you build a continent in like the Andes or Tibet, you move along this path. And then eventually the continents will relax to their stable parts, the shields that we have here. And they will deviate from this orogenic path, coming off and basically sinking. And there's something else besides erosion that is operating here, because erosion only will take you straight down right here. So there's a hysteresis problem right there. And so what are the other processes that can take a mountain down? Well, one is just thermal relaxation. And we know this process works very well. This isn't, this is a new paper, but Sclater back in the 70s, one of the most interesting things ever done in earth sciences was just to plot things like depth versus age of the seafloor. And it goes with the square roots of age, that's what here or there, or the heat flow goes with the square root of time here. And what that is showing you here is that that can be explained just by the conductive growth of a thermal boundary layer with time. Very simple. And the time scales for that are here. The thickness divided by the thermal diffusivity. This is why ocean basins sink. They start off high, 2 kilometers below the seafloor. They go eventually to 4 kilometers below sea level. That process, certainly it must have happened also with continents. They start off hot and they must cool, right? So if we apply that to continents too, then, well, this is basically showing you this. Here's the crust, here's the thermal boundary layer. Now, the thing is the chemical boundary layer is actually in here. It's still hot, right? But it's rigid, so I didn't draw that in there because it's still hot. But it's there. It starts off in this orogeny being 200 kilometers thick. But with time, it'll cool. And the time it takes to cool to the base of that chemical boundary layer is going to be with a scale as follows. So this would be the chemical boundary layer thickness, 200 kilometers or so. So when we talk about the life of a continent, they go up like this, and thermal boundary thickening takes you down. And so when you land here, it's a combination of these two, and it just depends on the relative timescales between thermal relaxation and your landform relaxation timescale, which depends on erosion kinetics. The fact that we're closer to here suggests the erosion kinetics, this timescale is shorter and more important than here, except when you get to really old ages or long times, then the thermal boundary layer thickening kicks in. So this is just showing you elevation versus crustal thickness, all the data now here. This is your orogenic path, and then I suddenly shut down mountain building, and I just let it relax, and following these fairly simple rules that equation I have, and then they will start to cool, and then and erode, and they will the crustal thickness will go down, the elevations come down, and then eventually, depending on how thick they can actually grow, that's the chemical boundary layer thickness, they will stop. Okay, so here's a 200 kilometer one, and depending also on the rate constants, it'll stop at different places. But you can see this one right here. You follow that, it keeps on going. And then eventually the thermal boundary layer thing takes over. And then we even predict that your mountain may even go below sea level. So continents begin as a mountain, but may eventually invert and become a basin. It's kind of weird, but we know from the great unconformities that actually must happen just from looking at the geology. So here, elevation goes down and it goes here. So this is how unconformities are made. In the massive erosional part, that's where you bring the deep crustal rocks up, the magmatites and so forth. That's happening during the crust formation event, the magmatism. That's the only time you can have enough erosion, because the erosion is driven by the magmatism, the high elevations and also. And then when the forcing stops, there's a long window here where you're above sea level and nothing's happening. You're dead, you don't deposit any sediments. It's only until you go sufficiently below sea level they can start to accumulate sediments. And that window is this missing history in the diaries of geology. And that's how they're formed. Let me skip this one, that's there. So great unconformities, that's basically that. So it's sort of a textbook thing, but sometimes these real simple things we take for granted and want to, it's good to really understand why. So continents are born by crustal thickening, and that's the time when the erosion is greatest. And after the forcing stops, they subside by continued erosion. and thermal relaxation, which eventually takes over. And the punchline is continents will turn into basins with time. They invert. So if they invert and they go into basins, the next thing we want to know is what controls how far they will go. What is that terminal resting state of a continent after they fully matured there? And that actually depends on the thermal state of the Earth and the thickness. Well, we've assumed that the thickness of these chemical boundaries are constant, which then means that really what controls it is how hot the rest of the Earth is. And so we think that the Earth has cooled with time, and you would think that in a hotter Earth, things are expanded, thermal expansion, everything should be higher, but in fact, the effect is exactly the opposite. So it seems counterintuitive at first, but will make more intuitive sense if I explain this. So here, this is temperature, and here is depth. This, for red line, for example, is the temperature of the mantle, the convecting mantle, and this line right here is the geotherm within the thermal boundary layer right there. And the difference between these two lines is basically that temperature deficit that will cause thermal contraction. So the thing you want to look at is the width of the area of this curve. That's how much colder the lithospheric mantle is compared to the mantle. And the colder it is, or the more relative colder it is, the bigger this area is, the stronger this anchor relatively is going to be. So you can see in a hot Earth, even though everything is hotter, this area of the triangle is much bigger and then when the Earth is cooler. So as a consequence, when the Earth cools, right here, for a given thickness of the chemical boundary layer, it's going to rise. Continents have to rise, okay? The only question is when. So they have to rise. All planets who have continents and a boundary like this will follow the same trajectory. They got to start off at some low elevation, and they'll eventually rise with time as they sit there. And so you can plot elevation versus mantle potential temperature for different crustal thicknesses, and that's the crustal thickness defined by the erosion ultimately and ocean volume. But you can see you start off at 1600 degrees, then they're going to cross over the sea level part right here at 1400 degrees, which is where we are today. And so what we can do is take that thing and convert it to temperature time histories. And these are Claude's data, actually, the red ones from this paper right here. And these are constraints made from peridotites using the same thing that I showed earlier. And you regress some lines to there, convert that to this temperature to age. And basically this is indicating that we should see an emergence. Here's 2 billion years ago. Continents should be below sea level, the stable parts of continents, not the mountain building active areas. But once they become stable, they'll be below sea level on average, and then they will rise above sea level around between 1 billion years and 500 million years ago. Keeps on going. One of the things, there are some simplifications in this model, so when you get way above sea level and way below sea level, I don't account for, especially here, I don't count for the deposition. So these are overestimated in terms of the depths. Okay. So what we predict is continents should emerge, and it should emerge late in the history of our planet, and in the latter quarter of our planet. And so what's interesting about that is, well, this emergence is a very slow thing controlled by the secular cooling of the Earth, right? And that's slow. The thing is, continents tend to be flat. Okay, so when they're flat, when you get close to sea level, you can flip back and forth very quickly between above and below sea level. It's an either-or thing. It's not a gradual thing. So although the continents are rising slowly from the secular cooling, with the question of whether you're above on average or below on average sea level, that's fast. That's a switch. So here's this gradual trend, but then the area of continents below sea level can flip within 100 million years, just like that, very quickly. Again, these are the stable parts of continents, not the active building regions. So just like that. So you have to imagine this is our planet today. The white areas are above sea level. The light blue areas are what I call continental shelves, the shallow seas. Today, the shallow seas only form a narrow ribbon around the continents. They're your continental margins. They're your shelf. Most places they can be anywhere from 10 to 50 to maybe at best 100 kilometers in width. You have to imagine that we have in our mind that continents should always be above sea level, but that's not true. All we have to do is drop the continents a little bit, and then you would have something like this, a very different world, and we'll call that a water world, where you'll still have lands, right? The lands are the mountain belts. They're always going to be high because you're actively adding magmas or compression. They're going to be 4 kilometers high. They're never going to be below sea level. But the stable parts, the ones that have stopped that, the forcing which has stopped, could all be below sea level. Okay, so this would be a world with islands, deep oceans, and the large, expansive, shallow seas, sort of epicontinental seas. In fact, for much of Earth's history, we know that just walking around, you'll see these Paleozoic, early Paleozoic sediments, Proterozoic sediments that carpet much of the continents. So today's world might actually be an unusual time throughout Earth's history. So what are the impacts of this? This is more going to the surface process here. One of the things is, like in the Precambrian water world, you'll still have your mountain building, you don't stop weathering, but those sediments will go to the deep ocean and as well as being deposited on the shallow seas of the continent. They just sit there and they don't go anywhere, and they're just kind of accumulating and getting stored. But if you have these things rise up, then soon it doesn't stop this will come, but then all of a sudden you will start this re-erosion or re-weathering or second generation sediments that were deposited here, and they're going to contribute back into the weathering regime. The difference is they've been sitting in here for 1 billion years or more, aging, right? And if you have radiogenic isotopes, they're going to record, they're going to age radiogenically. And so what you'd expect in things like strontium isotope of seawater is that a prediction that when the continents emerge, there should be a very rapid rise in the strontium isotope composition of seawater. So this is that in seawater. You can see it's quite scattered in here. But as you go to, so here we talk about Tibet, right, rising. But the largest sustained rise in strontium isotopes happens here between 500 million years ago and 1 billion years ago. And to this day, there has been no explanation for that. One possibility I would suggest is maybe this is when the continents are emerging and then releasing all this detritus that they've been accumulating over many, many hundreds to billions of years. The other implication of this sort of continental emergence is, like I said, it's black and white. You're above or below. However, you can imagine, like the stock market is, there's always a trend, gradual long-term trend. So you should watch that. But on the short term, it's going like this. And if you're a day trader, that will drive you mad, and you'll never win that system. And the continents, I mean, the secular cooling of the Earth is probably not just like that. There's regional effects. There's going to be some bobbing up and down. But if you're right close to that threshold, you can flip back and forth between water and terrestrial world very quickly. And the effect of that is potentially profound, because in the water world, you have less continental area to erode, so that silicate negative weathering feedback that draws down CO2 is going to be less efficient. But when you get into a terrestrial world, it's going to be far more efficient, right? So what this is based on Jeremy Cave's work. This is PCO2, normalized to today. And this is the carbon inputs or outputs. We're assuming steady state there. And these curves are basically the strength of the negative feedback for chemical weathering. So the way to look at these curves is for a given production of CO2 from volcanoes and metamorphic to gassing. If it was this yellow curve right here, this would be the steady state PCO2 in the atmosphere. Okay? But if you have emergence of continents, this would be a water world where you have very low sensitivity to weathering. The weathering feedback has low sensitivity to CO2. To a emergent world, you go to a green one. And so for the same CO2 inputs of pumping through volcanism, so we don't have to do anything with changing volcanism, but you just have continents move up a little, you would flip from here to here. And your steady state CO2 would go from very high greenhouse type conditions to icehouse conditions. You can go back and forth, okay? And so indeed, around that time, there are these curious snowball Earths. There are very long windows of time where you went complete snowball, then you went to a greenhouse. Still no really good explanation for that. Thousands of, well, maybe not 1,000, but lots of hypotheses. So I'm going to add one more hypothesis to that maybe is just related to the Earth. And finally, I'll end with some implications for phosphorus cycling. This also has implications for oxygen, but won't have time to talk about that in detail. But if we look at phosphorus cycling in the oceans today, right, what actually happens is you have upwelling and nutrients, the phosphorus is supporting biological productivity up there, and then they die, and all this material comes down, and it can get preserved if it can get buried before it becomes fully oxidized. And so in the deep waters, as you go down, it burns up, all the organic carbon burns up and remineralizes that phosphorus before it actually gets buried. But today, so it turns out only in the shallow areas where you get this, because that's when your sort of oxygen minimum zone intersects the sediments, okay? And so if you look at today, here's the percent area of continental, the open oceans, and this is the continental shelves that we have today. It's less than 10%. But almost all the phosphorus, at least 60% of it in the oceans is sucked out in these shallow margin, seas today on the fringes of the continent. So you've got to think of these continental margins as really greedy for phosphorus. We'll go back to a world in which you drop the continents and you have continent-wide shallow seas. So suddenly you have 100 times more greedy guys for phosphorus. Then that means that the phosphorus concentration in the seawater is going to be fundamentally changed. The availability is going to be changed. So in the Precambrian world, the efficiency of the phosphorus thing is going to be very strong because it's distributed across all the continents, leaving less phosphorus to be available in the oceans. When you go to a Phanerozoic world, it's only concentrated in here, and so less efficient, allowing to have more phosphorus in the oceans. At the same time, you have reweathering of these ancient sediments that amplifies the source. So we can predict based on, with the same things, this is the area of shallow seas from the secular cooling there, and this is the amount of phosphorus in the oceans. So in the Precambrian world, it start here, in present day it'd be here, so you can increase almost by a factor of 10 the phosphorus into the oceans. And this calculation doesn't even count anything about additional sources right there, so it can be even greater. So that's interesting. A fundamental change in the phosphorus cycle. Is there any evidence for that? Well, if you look at phosphorus ores in terms of tonnage here versus age here, you see that all these big phosphorite deposits all occur 700 million years or later. There's something going on here too, but that may be, we can talk about that later if you want. But here's the drop in the area of the shallow seas, and then here's the phosphorus concentrated in seawater. And when that goes up, what you would actually get is, although there's not much phosphorus in the seawater over here, the problem is the phosphorus is shared between all the shallow seas, so you cannot build up any concentrated ore deposits. In this area, because it's concentrated in the margins, you can build up very phosphorus-rich sediments, even though it's not as efficient as pulling out phosphorus from the ocean, so phosphorus is allowed to rise. So could that be, we have the Cambrian explosion here, the rise of oxygen, could that have had some relationship to life, because you fundamentally altered nutrient cycling, a deep earth control? I don't know, but it's worth speculating. This is a very peculiar observation. So that's it. I'll end with that. Basically, the story of a continent, it begins with this mountain building event, a rise, and then they fall, they become basins, and then eventually they rise back up again to where we are today. Thank you.
Any questions? Benin.
What controls this magic thickness of the lithospheric mantle? Why 200 and not 3 and not 1?
Oh, I have no idea. We just take it as is. That's what they are. Now, it may not be exactly 200. So this is simplified. there's some that are 100, some 200, some maybe a little bit greater. But what's clear is you don't have 300 or 400 kilometer ones. Why does that not happen? I don't know.
But is it fair to say that there is a magic thickness that seems to be uniform for all stable?
I think there may be a somewhat magic thickness, yeah.
And have to make by the process of making this black.
Yeah,
Can I
it could
come in
be.
here?
Yeah.
There's you know, a lot of these xenoliths are old, 2-3 billion years old. But when you go into the North China Craton, for example, some of the work that's been done is really changing our ideas on that, because this looks like this stable thermal boundary layer, this very thick one, is gone. And so it used to be thought that this stuff was forever, somehow. And now we're starting to see that
some can be destroyed.
Some can be destroyed. So that might be an interesting thing to think about. So perhaps the stuff was even thicker. It thickened at some point. It was probably early.
Yeah.
And so this 200 kilometers is what it is today. And it might have been thicker in the past.
Yeah, it's definitely fair to say that they could have been thicker. Could have been thinner too. But the continental crust for sure was thicker. That's, yeah. Mm-hmm.
Linda?
Anything about the phosphorus ore that simply
I have no idea on those. I think what I was going to say is some people say, well, nice story, but what about those phosphorus ores 2 billion years ago? I'm going to be completely speculating here that something similar could have happened there. So one of the things that in this community we're arguing about is some people think the emergence happened 2 billion years ago instead of later. And in fact, when those guys who wrote that, they kind of, I don't know if they talked about the phosphorus, but they predict the same thing with the strontium. So they don't see it in the strontium, so they argue that the strontium data is not good. But I think you would predict the same thing with phosphorus. Now, it turns out around 2.5 billion years ago, that's when a lot of new crust was formed. So it could be that all of a sudden you had a lot of continents above sea level at that time. And then, but it's a temporary effect because they eventually die down and then we start over this whole process. In this case, they come up not because of continent building, but just a secular cooling. So all my calculations, I start, by the way, really after 2 billion years. So there are obviously many assumptions in these calculations. One is how the continental area has changed, how the ocean volume has changed with time, and I've assumed those to be constant. So after 2 billion years, I feel maybe kind of okay with that, but before that, definitely not.
So what makes the rate of crystals in 2.5 billion years very high, then slow down so that is that something that about the crystals at 2.5 versus the ones that sort of stay around the ones that
I think so. For whatever reason, these 2.5, 2.8 billion year old continental crust, they're the ones underlain by this very unusual mantle root. And then after that, we don't seem to generate those thick roots. Yeah.
In the Coronaga model, he would say that this time 2.5, this is a time when you had when the rate at which the mantle was heating up from radioactive decay kind of reached its peak, and it far exceeded the rate at which this could be dissipated by convection. So you get this, so there's a model out there, and it seems to go well with metrology, but this is a thermal maximum. So if you go back in time even further, then things were cooler. You go forward in time, things were cooler. So it was a very active time. There were a lot of people have written papers on why was it so active. So there was a burst of magnetism.
Some unusual, it was unusual at 2.5 to 7.
How would you get the first continents?
If the only magmatism is basaltic.
You're only making melting fluid, making thick oceanic crust. How does that? What's the process to making those?
Or you mean making granitic stuff? Yeah, I mean, so I actually, I define continents not based on composition, based on thickness. I have no problem with a basaltic continent, but yeah, I mean, the continents that we know today happen to be granitic, and so I guess the question is, how do you generate these granitic rocks, and has that changed through time? There's a number of work out there that would suggest before 2.7, most of the crust was basaltic, and then it became more felsic with time. I think water is a critical thing. I think thickness is another critical thing. So water expands the fields over which you can generate a lot of silicic magmas. If you don't have a lot of water, I mean, you can generate a rhyolite from dry basalt, but you can't generate much. But you put water, you generate far more. And then thickness helps because you get these garnet peroxenites. So we have a paper coming out in a few weeks in Science Advances on this, and that'll drive silica enrichment a lot. So that combination. So that probably requires a mobile lid, if you want to call it plate tectonics. The water probably you need to recycle material in, and if you have a stagnant lid, I think what Claude was alluding to, you probably can't do that.
Yeah, there's a literature just emerging on this problem. I mean, you start off with basalt. You don't, and it's the residue that stays behind it is all in the rocks. Well, how do you go from basalts to granites? And so a popular model is that you hydrate it. So you build these up, you hydrate it, and then either founders through the subduction type process, or you're just stacking hydrated stuff. So you're going from basalt to a metabasalt, so it's amphibolite essentially. And the melting takes place at the base of the thick crust. So it's basalt plus water plus heat equals granite. I mean, you can do this experimentally. The question is, how do you do this in a tectonic scenario? Well, I mean, that's the big question. Is it really like modern day like subduction, or is it, I mean, another term is sag adduction, just sags, drips, or?
Well, how you keep it there, I mean, these eclogites will go down, but I've always thought once the continents erode down to sea level, there's no more erosion. So you can't get them into the subduction factory. So it may be as simple as sea level controlling that part.
Your model, you basically add material to the crust and add causes it for thickening and erosion.
Yeah.
What about places where you have like delamination occurring, where you're increasing the lower crust?
Yeah.
Change the thickness and cause elevation too.
Yeah, that would have an effect too. Yeah. I mean, the eclogites would of course pull you down, but then when you remove them, they come back up. I didn't include that in most of the modeling. It turns out for the really high magmatic flux events, if you don't put the eclogites in that formation, you will generate mountains that are just crazy high, like 8 kilometers, on average 8 kilometers high. We know we don't have that, so it plays a role for sure. And so, if you look at that elevation versus thickness curve, although there's this correlation, there is scatter around there, and some of that could be delamination, asthenospheric support, all of that. Yeah. But I still think the buoyant parts of the crust that the low density one, that thickness is the dominant signal.
Any more questions? We have time for one more, I think. Okay, well then, thank you very much, Cynthia.
Thank you.